You ever get that feeling that some of the most complex things in the world are all secretly playing by the same set of rules? Well, today, we're going to pull back the curtain on a hidden language, one that connects puzzles, your online security, and even the fundamental laws of the universe. So yeah, let's dive right in.
All right, to get us started, I want to show you three things that, on the surface, have absolutely nothing to do with each other. Our job is to figure out the invisible thread that ties them all together.
First up, an icon. You know it, you love it, maybe you've thrown it against a wall. The Rubik's Cube. It's all about those twists and turns, right? And trying desperately to get back to where you started.
Next, something you probably see dozens of times a day without even thinking about it. That little lock icon in your browser's address bar. It's the symbol for the incredibly powerful cryptography that's protecting, well, everything in your digital life.
And finally, let's go big. I mean, really big. We're talking about the deep, elegant laws of physics, those bedrock principles like the conservation of energy that govern the entire cosmos.
Okay, so let's just pause for a second. A toy, a digital padlock, and the rules of the universe. What on earth could possibly be the common thread here? I mean, really, what's the connection?
Well, the answer isn't a thing you can hold in your hand. It's an idea. And it's an idea from mathematics that was designed for one specific purpose, to study the very nature of symmetry.
And that big idea is called group theory. Now, don't let the name scare you. This isn't really about numbers and equations in the way you might think. It's about actions, a twist, a reflection, a combination. It's a language for describing the rules of structure and symmetry, no matter where you find it.
Okay, so here's the formal definition. Group theory is a part of abstract algebra. But let's just break that down. All it really means is you've got a collection of things, a set, and one way to combine them, an operation. And this is the crucial part. For it to be a true group, it has to play by four very specific, very important rules.
And here's the beautiful part. These rules are actually super simple. First, you've got closure. This is kind of the vaguest rule. What happens in the group stays in the group. Combine any two actions and the result is still a valid action in that same group. Second, associativity. It just means it doesn't matter how you group things. Third, identity. This is the couch potato of the group. It's the do-nothing action. And finally, my favorite, inverse. This is the cosmic undo button. For every single action, there's a perfect and opposite reaction that takes you right back to the start.
Okay, so that all sounds pretty abstract, right? Rules and sets. So what? Well, let's make it real. Let's circle back to our first mystery, the Rubik's Cube.
And it's not just me saying this. As Janet Chen from Harvard's Math Department puts it, all those possible twists and turns on a Rubik's Cube, they aren't just a random mess of options. They actually form a perfect mathematical group. So let's check the boxes, shall we? The set is just every possible move you can make. Do we have closure? You bet. Twist the right face, then twist the top face? That's just another sequence of moves. It's still in the set. Is there an identity move? Yep. Just don't touch the cube. Doing nothing is an option. And the big one, is there an inverse? Of course. Every single twist has an opposite twist that undoes it. It fits the rules perfectly.
And here's why that is so incredibly important. The number of possible scrambled states of a Rubik's Cube is, well, just look at that number. It's 519 quintillion. It is mind-bendingly huge. You could never, ever solve it just by randomly trying things. But because we understand the group structure of the moves, mathematicians can create these incredibly elegant algorithms that can find the solution from any position. Group theory doesn't just describe the chaos, it gives you the map to fix it.
Okay, so we've gone from a toy to a tool for finding order. Now, let's shift gears from puzzles to privacy. How in the world does this same idea help keep our digital lives secret?
The secret sauce behind almost all modern cryptography is creating what we call a one-way function. Think about it like mixing paint. It is incredibly easy to swirl two colors together to make a new one, right? But trying to unmix them back into the original two colors? Yeah, good luck with that. It's practically impossible. Group theory provides the perfect mathematical recipe for making these one-way streets.
One of the classic recipes is called the discrete logarithm problem. Now, the name sounds way more intimidating than the idea. Imagine I take a number, raise it to a secret power, and do a little bit of modular arithmetic. It's lightning fast for a computer to find the answer. But if I only give you the final answer, trying to work backward to figure out what my secret power was is ridiculously hard. That's the one-way street. And it's the specific group we're working in that makes it so tough to go back.
And what's really fascinating
is that the kind of group you use makes a huge difference. Early crypto systems used groups that were, mathematically speaking, fairly simple. They worked, but you needed really big, clunky keys to make them secure. Today, though, we use much more complex, exotic groups based on something called elliptic curves. It's like a twisted, more clever form of geometry. And because the one-way problem is so much harder in this group, we get the same level of security with much, much smaller and more efficient keys. This is literally why your phone can handle super strong encryption without its battery just dying on the spot.
So, we've gone from a puzzle to a password. That's a pretty big jump. But now let's zoom out. Let's zoom all the way out to the biggest canvas there is, the universe itself.
It turns out, this language of symmetry is spoken everywhere in science. In physics, there's a truly profound discovery called Noether's theorem, which shows that for every deep symmetry in the laws of physics, there is a corresponding conservation law. So the fact that the laws of physics don't change over time, that's a symmetry, is the reason energy is conserved. Whoa! In chemistry, the symmetry of a molecule's shape completely dictates how it behaves. And in pure geometry, group theory is the ultimate bouncer. It proves why there can only be 5 perfect 3D shapes, the Platonic solids. The rules of the group literally forbid a 6th one.
Think about tiling a floor. On a normal, flat, Euclidean surface, you can only tile it perfectly with regular triangles, squares, or hexagons. That's it. The group of possible symmetries is really restrictive. But if you were in a different kind of universe, a curved, hyperbolic space, the rules of the group change. They become richer. You could tile that space with perfect pentagons, or heptagons, or any regular polygon you want. It's like different groups create entirely different realities with their own unique rules.
This gets to such a fundamental point that the mathematician Felix Klein argued that this is what geometry is. He said geometry is simply the study of which properties of a space stay the same, or are invariant, when you apply a specific group of transformations to it. So group theory doesn't just describe the rules of geometry, it defines it.
So after all that, from cubes to crypto to the cosmos, what's the big idea here? What are you supposed to take away from all this?
Here's the most important thing. Group theory isn't just some obscure, dusty field of math. Think of it as a lens. Or better yet, a superpower. It's a new way of seeing the world that lets you spot the hidden structures, the underlying patterns, and the secret symmetries that connect the most unexpected things.
Once you start to learn this language of symmetry, you really do begin to see it everywhere you look. So I'll just leave you with this one final thought. Now that you have the lens, what hidden symmetries are you going to find?